Hello, hello, hello. I will be your slide reader for today. Let's see, is this working? Is it? Uh-oh. I spend all this time on the clicker and then it doesn't click. There we go. No, it was just in the wrong mode. All right. I'm the Wizard Tower on Twitter and GitHub. Adam McCullough, first and last name squished together on LinkedIn. I'm currently job hunting, so if you want an opinionated Haskell or a Rust person, give me a call. So what this talk is about is benefits and trade-offs of using different technical approaches. And also, not just evaluating them in the sense of, oh, does it work on my machine, but how does it work in a larger scale? So how will it work for other people to pick up this language or use these tools or work with these idioms? The problem with doing this is that tech is very fashion-driven, and people write a lot of very, very empty thonk pieces on LinkedIn that tell you absolutely nothing but spend 15 minutes doing it. And so I want to spend some time to try to give you some better intuitions for how to make better decisions later on. So what this talk is not about is asking what's best in life, because Conan did that already. But also, asking questions in a moral context is a very, very good way to get yourself completely wrapped around an axle. Some of the greatest minds that humanity has ever produced tried to sink their teeth into this question and kind of got nowhere. It's not that these questions aren't worth asking, it's that it's very easy to get stuck in a cul-de-sac that just goes round and round and round. So we are going to be confining ourselves to largely an economic way of thinking. So if we want to achieve this goal, how much is it going to cost? What is it going to do for us? What other things could we'd be doing with our time and resources? The thing about being an engineer is that we have to be tragic people, frankly. We have to look at the world in terms of people want a lot of things, but they only have so many resources. And so we have to make trade-offs. And that also means that if we're examining something, some new hot piece of tech, we have a responsibility and an obligation not just to look at the rhetoric and the sales copy, but look at how it actually works. For example, I think type systems make development easier and make it easier for engineers to work on code with confidence and not ship bugs, but that's not always the case. The solution to every problem is not add more types. Another way to frame this, if we're going to economics, is that you can't say that, oh, we need to achieve this no matter the cost, because that's just getting yourself back into the same loop of you're abusing one set of people for the sake of another, or you're robbing from this cause to achieve that other one. And doing that blindly and without critical thought and mindfulness just digs you deeper into a hole. It doesn't make things better overall. So, all right, we're looking for ways to spend our creative efforts wisely. What's a good real-world example of that? Well, I think one real-world example is stop signs. The great thing about stop signs is that they're kind of dirt cheap. If you get the really high-end ones, the ones that are very reflective and very large, they cost, for one, about $130. And that cost goes down very, very quickly as you do bulk orders. They require basically no maintenance or supervision. You stick them in the ground, you make sure it's solid, you walk away. They're self-policing. And provided you are using them honestly, and I'll get into this in a little bit, they're actually quite effective. They stop accidents. They are very good at making sure that people drive safely, and they're aware of what's going on, and they're warned about hazards that they may not have been able to detect. What I mean by this is that there's something that happens, especially in residential communities, where they're like, I want to slow the drivers down. And so they'll create artificial stop points where there isn't really a need for it, thinking that, oh, this will slow people down. And what actually happens, and there are studies that you can cite this, is that people feel like their time is being robbed and they are being cheated. And so what happens is that they'll stop, they'll accelerate more to make up for lost time, they'll brake harder at each stop sign, and so it creates more hazards. And this is the kind of emergent property and behavior that we want to try to avoid when we're working with our code bases and making technical decisions. A middling example is roundabouts. So roundabouts, there are a lot of studies that show that they reduce injury crashes. So not only do they reduce crashes, but when crashes happen, they are less harmful to the people in them. They also improve traffic flow, meaning that people get to where they're going quicker and they're spending less time on the road. And there's a citation for that. The downside is that putting down a stop sign is about $130 material and hiring someone to dig a hole. Building a roundabout is a little harder. You kind of have to tear apart the old infrastructure, that whole intersection, for quite some time to rebuild it in the proper way. In addition, I think this reflects nicely on monads, is that there are a lot of benefits, but it's very intimidating for brand new developers, or brand new drivers. Like you can explain the premise of it's a four-way stop in about 5 lines to a new driver. A roundabout is much more of a dance. It's, once you know how to do it, you wind up being safer, but those first few times are very white knuckle. All right, what's a bad example? What's an example of where we're really not being wise with our money? How many people flew here today? Yeah! So, okay, let's dig into it. We can't argue with the TSA's goal. Stopping hijackings, stopping terrorism, making flying safer. These are noble goals. Okay, cool. But first off, the TSA costs a lot of money. The last budget that I was able to dig up is that it costs $9.8 billion a year to run. Okay, fine. Government programs tend to cost a lot of money. That's not news. How effective is it? Well, glad you asked. So, DHS ran a secret shopper test where DHS agents went to an airport, posing as regular people, smuggling in weapons, seeing if they could get them past TSA. The data on this is a little bit vague, but what they have told us is that their failure rate, meaning that the agent doing the secret shopper test, their success rate of smuggling a weapon past TSA was somewhere between 80% to 95%. So we're spending almost $10 billion a year for something that works one time in 20. Not quite as effective as stop signs. And here are citations for that as well. All right, let's dive into some tech examples now that we've got an intuition built up. Let's start with error handling in Go. This is great. So we import some libraries. We try to open a file name. Go helpfully hands us an error type. We check if it's nil, if it's not nil, and then we call log.fatal with what happened, which also helpfully exits our code. Cool. Let's look at another way to do this in another very, very production-ready systems language. Let's look at Rust. So we have to do some weird ceremony on line 4 saying, hey, main returns this weird result type that we get from a crate somewhere. That's bizarre. And we say, all right, hey, open a file. It's called foo.txt. And that little question mark at the end of line 5 says, if this went wrong for some reason, just return. Like I need something in this file. If it's not there, I can't keep going, so make the pain stop. And if it's a happy path, then keep going. What are the differences? Well, the nice thing about Go is that it's very manual, meaning that it's very easy to explain to a newbie. The problem with Go is that it's extremely manual, and so you have to recite this ritual every single time, which means it's very easy to get wrong. Not only is it easy to copy-paste the function wrong this one time, but it's very easy to lose sight of where you are and what's going on and what this error means on a semantic level. And so it's a lot harder to decide, do I need to return? Do I need to keep going? Do I need to throw an exception? Do I need to tell someone that the nuclear launch codes have been leaked? It's harder to tell. And not only that, but even if you have the linting turned on in Go, which says, hey, by the way, this thing returns an error type, and you're not checking it, it's easy to lose context of it, so you can either forget to check if you don't have that linting on, or just throw it away to smother the linter and get the PR merged. And again, you're trying to have to recreate these idioms and decide what to do at every call site. And there's no graceful default path that you can figure out, oh, this is the one place where I need to do something else clever. You need to make that decision over and over and over. Who knows what the billion-dollar mistake is? Yeah, of course. Okay, for those that don't, I forget who said it, but Tony Hoare, yes, that's right. See, once I'm under the lights, I lose 20 IQ points. He was saying that having null be a universal inhabitant type and not making people learn how some types work has cost people, at the time, $1 billion of lost productivity. Even if we account for inflation, this is almost certainly a gross underestimate at this point. But Go, in its infinite wisdom, decided this was the perfect thing to do because, engineers can't learn new things, even though, as we've heard in other points in this talk, some types were around since '68. But again, new things, engineers, they're scared. Now, it's not like Rust is a miracle cure, right? Rust still has to deal with these problems. You still need to detect and handle failure. Things can still go wrong, and you need to decide what to do when those things go wrong. But there is a default language idiom that is very sensible of, if something has gone wrong and I can't get the value that I need, gracefully return and tell the caller function, hey, something went wrong, I'm sorry. And you can propagate that all the way up to main and the calling operating system if you so choose, which I think is pretty great. I think that's a very sensible default. And if you have another thing in mind where it's like you're parsing a file and one record in it was wrong, you can say, all right, I'm deliberately saying I'm not going to process this file. I'll record it somewhere else. I'll put an error message, and I'll try the next one. Fine. But you're allowed to do that here, but you have a very sensible option if something went wrong and I can't keep going. And this is one thing that I really like about Rust. Out of the box, it will tell you if you're discarding an error message or a failure. With Go, I think, at least the last time I tried it, which was fortunately a while ago, but the compiler will just silently accept it and swallow it and move on. You have to turn on a whole bunch of linting to say, hey, by the way, you missed something, which now I'd argue that Rust's approach is more type safe and also gives you a very easy ergonomic way to do the right sensible thing without spending a ton of overhead, without spending a ton of cognitive or creative overhead at each time you'd have to recite this ritual. And the compiler helps you when you mess up, which, given that we're all human, we have limited time, limited understanding, is going to happen a bunch. So that's one point for machinery making life easier. That's cool. Let's talk about threads. I'm not evaluating whether threads are good here. I'm setting up some groundwork to justify later things. What are the advantages? It addresses the end of the free lunch. That is the idea that we can't just rely on CPU clock speeds to get faster to make our code better. Things have been sitting around somewhere between 3 and 4 gigahertz for the last 10, 20 years. CPUs have been getting more cores, but they haven't been getting faster unless you do some really crazy overclocking and nitrogen cooling, and at that point you're no longer doing industry scale stuff. There's the potential for very fast code if you do it right, and it can, if you are very disciplined about it, create code that is both more responsive, because the thing that's listening to user input and the thing that's doing the heavy lifting are separate. And it means that you don't need to interleave a whole bunch of checks of check for user input and then read the DVD and then see if there's an input over here and then write this to a file. You can just do that all as 4 separate things that are running in parallel and concurrent threads. So that's cool. What's the disadvantage? Well, boom. The possible states in your program explodes. It goes up enormously, which means that debugging it is hard, and also race conditions are a thing, and also reproducing those race conditions is a thing. And so works on my machine won't fix kind of becomes the norm, which is not great. And also, it's not a guarantee that it will speed things up. If you are doing one thing, telling it to split these things off into 5 things, I guess this would be 8, I can learn to count, means that you now have 8 threads to keep track of, which means there now is not only the task of doing the thing that you want to do, but also the overhead of keeping track of all of those threads. So it can actually slow you down if you're not careful. And don't take my word for it. Ericus Raymond made this exact argument in Art of Unix Programming. Fun fact, when I read this, I was working on managing the pushes and releases of a 10 gigabyte C++ file that was aggressively parallel and concurrent. And we were kind of having a hard time with it. And I was like, oh, that's why. Okay. So this is why I'm saying I'm not evaluating. It's a necessary primitive, but unless you are unless you are either a hero-grade engineer or very, very familiar with the code base you're working on, it's very easy to get things wrong. There are things that help, things like having variables be immutable by default, move semantics or the borrow checker, depending on which generation you're coming from, or doing the Haskell thing of, oh, you want a copy of this data structure. Here, let me just make a new copy for you. I know that's not exactly what's going on. It's doing some fancy tree things under the hood, but Okay, hold on. I'm claiming facts, not evidence here. Let's look at immutable by default. Is this a benefit? Well, it turns out copying things all over the place is bad for both time and space complexity. You're using more RAM, and you're using more CPUs to outright that RAM, which is not great. Well, I mean, it's great for AWS if you're charging for compute, but if you're the forced sucker paying for it, you're not happy. And not only that, but side effects are why we write programs. Like the point you made in your talk, Babbage put a printer on the thing for a reason. If all you're doing is running code, you're just making a machine warm. There are things that do that are a lot cheaper. They're called space heaters. They don't cost $3,000 for a personal use one. So you're doing the thing that really pisses people off, which is you're adding a ton of ceremony to something that has to happen a lot, which, unless you have a tremendously good reason, is not a good thing to do. But as it turns out, we have a tremendously good reason. Sorry. Mutation is where bugs happen. Race conditions especially, but that's the next section. So yes, there's ceremony, but the benefit is that you rule out whole swaths of your code base as saying this is not the source of your problem because the value was set once and has not been changed. And it also means the few places where you are mutating things all over the place are where you need to spend your debugging efforts. It's drawing a big red circle around where your problem probably is, which is really helpful, especially as your code base gets larger and more people are working on it. Rust is also very good at detecting both kinds of errors, namely, this mutation or this variable or borrow is declared mutable, but you never change it, so don't. Or you're trying to change something that's immutable, knock it off. That also leads us nicely to the borrow checker, move semantics. So what are the disadvantages of it? It is an enormous amount of ceremony, and the first time you come across this, you're going to be bashing your head against the wall and trying to figure out why the hell does this thing not do what I want it to? When the first time I ran aground on this, I was writing something for my day job. And I was like, oh, this will be fine. I'll just, close my eyes and pretend I'm writing Haskell, and it'll be great. It wasn't. And I was like, what the hell is going on? And so I had to spend a lot of time trying to figure out what this thing was doing and what I was doing wrong. It felt like about the same amount of effort and complexity as learning monad transformers for the first time, which the first time you do that in Haskell, you are not going to have a good time. I will say one of the things that I'm very impressed with in Rust, the error messages were far more helpful than the ones from MTL or transformers. I got up to speed a lot quicker with this than I did with monad transformers. So the folks over at Rust did a very good job with the error messages. They helped a blockhead like me figure it out pretty quickly. It also demands a lot of upfront work to get your design up and running, which if you just want to figure out if something works, that's not great. That's not fun. And also things where you can imagine like, oh, I've done this in other languages and it was really, really simple. It could very easily turn into an enormous refactor here, depending on what you're doing and how you're doing it. Of course, the reason it's easier in other languages is that they're lying to you. What do I mean by that? The biochecker is there not to make sure that you don't leak memory or you cause some kind of incidental suboptimal thing. It's there to make sure that you don't create a race condition in your code. And that race condition would very easily cause either a logic error, like what you were saying earlier, of depositing money without debiting it from somewhere else. So you're just creating money out of thin air. It's trying to get you to squish bugs that you didn't know was there, which is actually a very helpful thing to do. And so it's more upfront work, and you have to think about it for a bit. But it means that things that pass that result are a lot more sound and production ready. And if you really need to, you can do the spooky action at a distance things that other languages do by default. It's just that Rust is going to ask you to put clown makeup on first, which I think is reasonable. Okay, fine, but the biochecker sucks. Let's talk about something really, really simple, like monad transformers. All right, let's look at accept T. Does it pay its weight? If we track failure of a computation with maybe, if we've turned null into a return type, shouldn't we turn I'm going to put a shotgun against the runtime and pull the trigger also into the type? Like, shouldn't you know about that before you call the function? I like this argument. I like this argument a lot. I think this is a noble cause. And since monads don't compose on their own, and we need monads in disguise, that's a reference, but we need monads in disguise to help with that, right? So that we can stack these things up. Okay, let's look at some code and see how that works. So I've written some amazing Haskell. We define myOM as the head of an empty list. We then force Haskell to evaluate it on line 4. And then we put line 5 to say, hey, we returned successfully. Isn't that great? And that's running in the IO monad. We have another thing that runs in the accept T monad that does basically the same thing. We're going to call these with catch, which means we'll have the function call and then the handler afterwards. And we want to be very clear that we're catching an error call in the handler and then return IO unit. So we'll take a message saying what went wrong and then the E, the error, and put that to standard error. And then we'll have some Haskell in main. We'll run the function in the standard function without the accept T wrapper, and then run it in the accept T wrapper, and then we'll have a print on line 13 showing that we caught both exceptions and gracefully exited main instead of having the runtime crash because we didn't catch one of them. So if we run the first function, of course, error gets called because getting the head out of an empty list is hard. And if we run the second function, we also get the same crash, which is not great. So what's happened here is that we've said that we want our exceptions to return a either, basically, of the return type that we promised or whatever went wrong, except that accept T doesn't stop functions from throwing exceptions or panics on their own. Those slip right past it. Now, all right, everybody knows that head is a stupid function. It should be rewritten. I don't know why they haven't, but let's look at another function. Let's look at opening a file, because that's the thing that programmers do. We're going to open cert not appearing in this talk.txt. And then we'll do the same thing in an accept T. We have to change our handler function to catch an IO exception instead of an error called, but it's the same thing. And our new main is catch these two new functions and change the descriptions a bit to show that we're actually running different code. And the nice thing is that the errors fill in the same slide this time, but the same thing happens. So this is a lot of machinery, that adds the complexity, both conceptually and time and space, to our code, but it doesn't do anything to stop programs or functions that just throw exceptions. So if you're not caught up on the new way of doing things, which the standard library isn't, you still have to deal with this problem. It's not taking any complexity off the table, it's just adding more. Well, okay, but let's look at some earlier code that we looked at. Isn't this doing what we want? So let's look at line 5. We're telling Rust, I want you to open a file with this name, and then that little question mark is if that doesn't go wrong, I can't keep going, so just return gracefully out. The nice thing about Rust is that they seem to have gotten this idea right from the get-go, probably because they stole it from Haskell, because that's what languages do. They steal all of our good ideas. And this works on what Rust calls a result or an option, which is either or maybe in Haskell speak. I think Scala uses the same name, so I'm not certain. Now again, Rust is not able to perform miracles. If you say, give me a file handle and unwrap it, right? Give me the file handle, that's giving you a result of file or error, and then unwrap it. If that's an error, you're about to have a bad day. Because what else can Rust do? But these functions are giving you a value to evaluate, not telling you to catch this thing. You don't have to wrap this in a try-all. You don't have to treat every I/O function as if it's about to put a gun to your head and pull the trigger. The downside to this is that the machinery behind this, the thing that's enforcing it, is vibes. There's no type machinery saying, thou shalt do this. There's no interface saying you have to do the right thing, and if the programmer decides to be dumb later on, that's their fault. So it is very possible to write code in your own application or write library code that just blows the head off the runtime at this first hiccup. And so you have to be very careful about how you're evaluating the code that you're using, both the stuff that you're merging in your own application, the libraries that you're using, and the libraries that you're shipping, to make sure that you're being a good steward and citizen, shall we say. So, it's a good idea. I like the sales pitch. I think it's a thing worth doing. But you have to be very, very careful about how it's done. Execution matters, not to make a bad programmer pun. All right. Let's look at some Yesod and Servant. Finally get into the thing that I promised in this talk. So Yesod is mechanically simple, I would say. It's doing some fancy things with template Haskell underneath the hood, but the code in it that you will have to read through, meaning if you're reading through the Haskell of the library, it's doing pretty simple transformations. You can reason about it and understand what's going on. It does some magic to glue different parts of it together with template Haskell, which, not my favorite thing, but hey, it tends to work. It's also built off of Y, much like Servant is. An important difference between Yesod and Servant is that Yesod makes it very, very easy to get the entire raw Y request. And so what that means is that if you have a question about the web request that you just got, you can get the entire thing right in your handler without any extra ceremony. Let's build up an example. So one of the things that's nice about Yesod is that it basically gives you a reader T out of the box. And so you can define what is data hello world here. You can turn that into a product type of here are all the things that I need to keep track of. And then I'll just be in a reader type that you can get to at every handler function. The make Yesod things on lines 3 to 5. The hello world in quotes is a template Haskell reference to the data type above. We have one root, that is the root for the root address. The postfix for the function we will look for later is home R. We support an HTTP GET, which means that endpoint will be handled by a function called getRemoteR. That's kind of the rules for how this works. We have to derive automatically an instance of Yesod for our hello world type. Our get home R handler returns some HTML with some helper stuff to create the default layout and express this very nicely, which is hello world. And then our main is telling Warp that we want to run the hello world server, really the data type, but again, that'll get glued together with the Yesod instance on port 3000 on the local machine. Okay, that was easy. What if we want to extend this and do something actually useful? Like, say, we want to have a post endpoint at /fancy that takes a JSON request body and does something interesting with it. What do we have to change? Well, let's look at our code. Data hello world stays the same. That's kind of it. We define a new endpoint. We define a new route. We define the function postfix. We say that we're going to support a post. I did change the column alignment a little bit to make it a little bit reader, but the code does the same thing. We have to define a type for ASIN to read in. So it's a struct that has a field called LambdaConf that is a type string, and we automatically derive a whole bunch of stuff. And then we had to write the handler function, which is fairly verbose. So we grab the Y request, we get the request body, we have a let binding for the result of the decode, telling ASIN, hey, I have this strict byte string, can you decode that into this record type? And then we pattern match on the results of that and say, hey, if we can't parse it, we tell the user, I'm sorry, that didn't work. And then if we say, okay, you think LambdaConf, fill in the blank. This is a security vulnerability. Please don't do this. User input is like the spawn of Satan. I'm just doing this for the example of a talk. So if we run something like this particular curl request, which is a post type, it's hitting this endpoint and has a content type of application JSON, and it's slurping in the data from that from a file, and that file happens to look like LambdaConf is awesome, the result will be, you think LambdaConf is awesome. Hey, that's cool. Let's do that in Servant. Again, we have a type, but this isn't something getting shoved into a reader T. This is the thing defining the routes that we have in our endpoint server, what arguments they take, if any, and what result we should expect. So we have one handler at the root of our server that takes gets and returns a plain text string. The item API proxy is boilerplate. That just has to be there. We define a server that maps the endpoints that were in the type one-to-one with the handlers of that type. And if you get that out of order, you're going to have a bad time. That's our handler. It's just returning hello world. This isn't returning HTML. This is just returning a string. Subtle difference, but worth calling out. Our main is a little bit more verbose. So we have a whole bunch of settings that we can derive. We have a make app function. We run that with these settings. And yes, the fact that it is binding on port 3001 was so that I could have both running at the same time. All right, we've got the hello world functions pretty much on parity. Let's define the JSON bed. So our root has to get a new endpoint. And we say that we glue, basically, the get handler with this new one. That's handling the /fancy root. It takes in a JSON request body of type talk_snark and returns a post plain text string. Item API stays the same. Server needs to know about the new function handler. Again, we have to define the record type. This is copy-pasted from the previous example. And the handler function takes a talk_snark and returns a handler string and does the same thing. Note that we don't have to handle the failure case here. Servant did that for us. If we handed in a request that wasn't parsable, it would just handle the error message on its own. So which one comes out ahead? Yesod is a lot less restrictive, which in a world where constraints liberate, liberties constrain, isn't necessarily a selling point. Servant's setup type, the server type, gives you a very, very clear specification of exactly what parts of the Y request it needs, in what order, and then what it's going to do to it if it works out. Yesod also does a whole bunch of weird magic with template Haskell, which could make it hard to read. That's probably not great. In my opinion, this is not the case. If I need to understand what any particular function in Yesod does, I have found that cracking open the source code and figuring out what it does was very, very straightforward. It took me a very long time to figure out how servants type families worked, because you have all the definitions over here in one file saying this is how you call it and this is the instance for it. And then what actually is how those are executed to process the interior Y requests are in a completely different area. And so if you're not already familiar with type family shenanigans, you're going to have a very, very hard time figuring out what's going on. And the documentation, at least the ones that I found, did nothing to describe this or explain it, which that was not great. I was not happy with that. As I said, they're in completely separate things. The other thing that servant does, which makes no sense to me whatsoever, is that there's no way to ask for the whole Y request. And there's also no way to ask for all of the query parameters, or all of the headers, or the full query string, or the raw query string, or a bunch of other things. I ran into this because I was working with a customer that had both, in the same server, they were using Yesod code and servant code together. And they were also, mysteriously enough, complaining about very, very brittle tests and very, very long build times. And I was like, yeah, no wonder. So they also were doing some things with client generation in servant, which Yesod does not support. And I was like, all right, I'll be pragmatic. I'll just switch them over to servant because I don't want to start digging into the bowels of Yesod and try to implement that. And then I found out that, well, there were a bunch of reasons why they were using Yesod was that they were doing a whole bunch of things that servant didn't do. And then I was like, oh, I have to dig into the bowels of servant now. This is great. And so I released a library that had these combinators. It was based off of the library was called Servant Combinators, and it was based off of a blog post where someone showed you how to do this but didn't put the code on Stackage. And I was like, all right, I'll write the code for the things I need. I'll write the code for a couple of other things that I came across. I'll provide examples. I'll add tests. I'll upload it, see what happens. All right, so if we're in Yesod, we need to look at an extra query parameter and a handler. If you haven't already gotten the Y request, you'd have to grab it. You'd have to make a binding of the extra query parameter that you need. So you'd have to interrogate that with a record function somehow. And then you'd have to alter the business logic to do something smart with it. That's it. You're done. You've touched one piece of code, and you've accomplished your goal. That's neat. In Servant, this becomes, well, you need to update the server type signature to say, hey, by the way, I need this extra thing. You need to update the handler type signature and make sure you update that in the correct way to make sure it's consistent with the server type. And then you need to update the business logic with it. And there's another problem. All of these have to be in sync. So the server type, the server definition where you're mapping routes to handler functions, and the type signature of the handler function. Congratulations, you understand how type systems work. What's the problem? Well, I'm not done yet, damn it. Type systems generally are very good at, you promised me an integer, you gave me a byte string. What the hell, man? What servant does is, you promised me a type of the name, and you gave me the entire definition, which if you have a root of like 150 lines means that you just know something went wrong because your terminal keeps scrolling. Which part of it is wrong? Have fun! There are ways to mitigate this. What I discovered, because I kept having this problem, because customer, is you break it out into modules, that are roughly sorted by category or common function. You can say, okay, I have all of these handlers, and they're defined over here. And in that same module, you define a local server type and server function. And then you export those out. And then where you actually kick the whole thing off, you have them in order, hopefully. You can glue those together. If something's wrong on the lower level, that will error out first. And if you get something wrong here, well, okay, if you get something wrong on the top level, you're still screwed because the error is going to be inscrutable. But you can do some clever things with like making it alphabetically sortable so you can at least spot a problem that way. And also have a bunch of documentation and comments saying this is a thorny problem, tread lightly. Anyway, adding a new endpoint, as we did, as I demonstrated, it's also the same kind of process. One other problem that I ran into is that if I need a lot of query parameters or a lot of headers, our endpoint type starts to look like this. And the function starts to look kind of like that. And oh God, did I make sure I get everything in the right order. Now, in theory, there is a way to get around this. You can do the same thing that you would do in a normal Haskell function of like, this isn't just a text, this is a first name and last name and address, and you can give it a more descriptive domain level name. But you have to define a to and from HTTP API instance for those. And again, this gets very, very deep into the weeds of type family nonsense that, or derive, if that works. It didn't when I tried it. Maybe that was just because our code was terrible. But I tried that, was not successful. And the hilarious thing about this to me is that having functions that take in a bunch of arguments, the obvious refactoring of that is you turn that into a record type. And as it turns out, Y already has one, so give it to me already. So, all right, let's look at the things that we've examined. What's the ceremony trying to achieve? Maybe optional, maybe / optional, is trying to solve the billion-dollar mistake. This is absolutely a thing that needs doing. Except T is trying to make this blows up the runtime explicit and also make it not blow up the runtime. It says that you return a value saying that something went wrong. You don't just hold a shotgun to someone's head and say, do the right thing or else. That's a good thing to aspire to. Immutable by default tries to make it so that if something goes wrong, you have fewer places to check. And it also means that writing parallel or concurrent code that shares values becomes a lot easier and a lot safer, which is good. And the biochecker is solving the problem that value ownership is hard, and especially mutation across threads is fraught with peril. I think Servant is trying to operate on the principle of least power. You don't get the entire Y request, you only get the few pieces of it that you ask for. I can understand that, but when I was working for it, it created a ton of paperwork, and it caused more errors than it solved in my experience. So maybe it works out. Except T is a good idea, but it's execution dependent. I think Rust nailed it. Again, let mut draws a big red circle around where bugs hide. Same with mvars and tvars and such in Haskell. Like, if something is changing a whole bunch, this is where you start like thinking very, very carefully about what's happening and where. I really like the biochecker. I'm really impressed with it. It took a while for me to bash my head against it, and I'm pretty sure my nose is still broken from it, but I learned a lot from it. And if you have to approach Rust with the same beginner mind and humility mind that you did when you're first learning Haskell of, I'm trying to do this thing, what are your suggestions? Please tell me what I'm not aware of, and help me write better code. If you come at it with that mindset, you will do amazing things that you did not know you were capable of. So, what was I saying? Oh yeah, how do you evaluate? You guys are smart people. Okay, have you ever seen the 2013 keynote at QuakeCon from John Carmack? It's been on YouTube for a while. Yeah, okay. This talk it's phenomenal. Well worth watching in its entirety. He covers a tremendous width and breadth of things, including digging into Haskell and writing his own rewrite of Wolfenstein in Haskell in 2 weeks because, God damn it, he's John Carmack and he's smarter than I am. One of the quotes that really stuck out for me, in particular in reference to this, is that programmers are extremely bad at doing the timescale integration of doing something they know is negative, which means it's only one global variable. It's only one go-to. It's only one thing that makes this thing harder to reason about and destroys equational reasoning. It gets you out of the bind. It gets the PR merged. It means you can go home. And now anybody else that tries to understand what the hell is going on is going to be completely lost until they read every single line, including the one that you got wrong. Programmers are bad at this. Programmers are also really good at making mistakes. Programmers will ship things that make absolutely no sense. The only thing stopping code from landing in a repo at a certain scale is, does the compiler accept it? Yes, no. That's not a great realization. That doesn't feel good to say. It makes us all, it makes it like, surely we're not that dumb, right? Well, as it turns out. Our job as senior engineers and architects is to try to counteract these tendencies as much as possible. If we can turn our code from something that is a source of tech debt and liability and to something that helps people make better decisions and creates a virtuous cycle instead of a vicious one, this is how we have to evaluate the technical and cultural choices that we make as leaders in the firms that employ us and pay us a lot of money. And a way to focus that question is, how likely is it that someone who needs to change something in our system will make good decisions, even if you aren't there to explain, answer questions, or review? If you can try to set this up, you will be in a very good place. Not to say that you will always succeed. Business is a chaotic maelstrom of madness. But if you're doing this, you're doing your job well. And again, what defines, in my opinion, a senior engineer boils down to two things. One, there are these ugly meatbags that want to talk to you about stuff, which sucks. They're not as polite as the terminal, but it happens. And two, evaluating in a clear, principled, and hopefully evidence-backed way the technical choices and trade-offs that you're making in your day job. Michael Soyman's 2020 LambdaConf is a great branching point for this. He's talking about the intersection of economics and functional programming. I think he anticipated a lot of how dour the LambdaConf talks have been here, but this is also well worth your time. That's it for me. You had a question. What's up? Oh, wait, hold on. Mike. Wait for a mic. I'm sorry.
Love your talk. Very philosophical in a good way.
Thank you.
I want to know, now that you've exposed yourself to Haskell and Rust, can you tell me which you like better without resorting to an answer of it depends?
I have the same though, do like Emacs or Vim?
Emacs, but I use evil mode, so ha. This talk is going to get me excommunicated from a conference called LambdaConf. Rust, no question. And I'm as surprised by that as no one is more surprised by that than me. I was, that brown bag I told you about, oh, Rust does, or Haskell doesn't have null, it's just an option. That was in 2013. I spent the next 3 or 4 years bashing my face against monads trying to figure out how to read from a file and failing. It wasn't until the Haskell book that Chris and Julie wrote, Haskell Programming from First Principles, that got me to the point where I could read and write and edit production code. I was like, this is the goddamn future. Why is everybody using this? I was in love. But writing code in Haskell was always a very like stop and go process because I had to figure out, oh, is this a string, a text, a byte string, a lazy byte string? Is this a rope because I'm using the new prelude/monad that my friend Andrew wrote that I contributed to? Like, there were a whole bunch of finicky details that stopped me from just hitting flow and doing what I want to do. And what I found with Rust is that once I have the I/O scaffolding set up and I'm just working with the business logic, I just write. And the program and the compiler tells me, hey, you missed this. You need to look at this again. That's not quite right. And by the time, like before I realize it, I've written like 3,000 lines of code in 2 days and I'm done. So I don't know why that is. It might be that I just wasn't smart enough to understand the whole referential transparency thing that all the Haskellers were talking about. It might be that I just didn't have the IQ to hit flow state in Haskell. But my experience with Rust has been deliriously joyful. I had a Twitter rant a while ago when the article about Microsoft rewriting a whole bunch of .NET code into Rust came by. And I was like, all right, I understand that if you're a Haskeller, Rust isn't quite up to speed yet because you don't have higher kind of types and you can't do your own monad. And I get you. I hear you, man. I love doing that. But given that the industry has been stuck on Java types or Python tests, or, hey, isn't C great? Getting Rust in mainstream adoption is like getting a warp core from the Enterprise D intact, just poof, here you go, kiddo, have fun. Like, the difference in like what the industry is capable of in like bog standard braces and semicolons languages blows my goddamn mind. Like there might actually be a reason to hope that people aren't just writing, hey, it does PHP work over and over again, because guess what? It doesn't. So that's my answer. And yes, sir. Oh yeah, Mike. See, you're smart.
Thank you. Thank you very much for your talk, and I cannot agree more with your first part, with your evaluation. It was really great. But I have a question about Servant and Yesod. I didn't look at them for at least 3 years. So are things getting better there, or is there like progress with these libraries?
So the project work that I did was from a few years ago that inspired this talk, the Yesod and Servant, and then I realized that there were other things that I could comment on. There is progress on the servant side in the sense that people have mutinied from the principle of least power idea that it was built on and showed you, if you need other parts that your servant thinks that you're not smart enough to handle, here's how you get them. The William Yao, I'm sorry if I got that wrong, it's on the README for servant combinators. His blog post showed you how to get out of prison, basically. But I think this is a conscious decision on behalf of the servant maintainers, and I don't see them going back on it. Interestingly enough, one of the things that Michael commented on when I was talking to him about this is that it would not be terribly hard to add the client generation feature that Servant has to Yesod. It's just that he's writing a bunch of Rust now, and so he doesn't have any interest in doing that anymore. So some, but the maintainers of Servant at least are probably a little bit grumpy about it. Sir. Yeah, no, Mike, so it's not least power. Okay, have I misread it then? What is it actually going on?
I believe it's honesty.
Okay.
Both Yesod and Servant are honest about the nature of the handlers. But Yesod's typing is ultimately also honest. We have a handler that takes in a request.
Right.
And does whatever the hell it wants with it.
Right.
Right? You could do the same in Servant. There's nothing to stop you from simply making a combinator that gives you the entire request and saying, I have a handler.
Yep, that's what my library does. There's a get Y request combinator that you can just say, give me the whole goddamn thing and get out of my way.
Right. But you've virtually lost all documentation about what you're doing with that request.
Yes, the problem,
To some degree, it's dishonest. Your cardinality is much, much, much larger than the truth of your program.
Certainly.
And so, because you've been willing to ingest what is essentially the equivalent of an any type as your input, instead of actually documenting what you want and how it is you're going to get it, right? You lose that. This is where client generation comes from, right? You lose the ability to document these types of specifications because your specification is fundamentally unprincipled.
Oh, sure it is. But let's dig back to.
So I don't think it's least. It's about honesty. It's about maintaining a low cardinality.
Right. What's the
Yeah.
principle here, though?
Your code is poorly written.
Right.
But it is in fact honest. You're taking in a bunch of text, you don't know what it is.
What else should I be doing here then? If I need to get a bunch of handlers, or
You're taking those headers because you need to build like a type for your underlying business logic. Whereas that underlying business logic is taking a parameter for which you could have an instance of something that parses from the header.
so what you're saying that so Paulo is saying that what I should be doing is teaching Servant how to pull out all the headers that I need into another type and then passing that into the function?
The fundamental issue with Servant that you're running up against is Servant's fault to some degree, right? But it's not by saying, oh, you're not smart enough. We're hiding this from you. We're doing this principle of least power. It's that to operate effectively in Servant, you need to develop the skill of making your own combinators, right? Servant to some degree is saying, here are the combinators we have for you. We wrote these
Oh, I
for
see.
you,
Okay.
right? It's a library of combinators. You can make your own. So if you would wish to parse something from the headers, it is in fact upon you to say, I have a combinator that takes in a list of text and figures out what to do with it in some appropriate way to construct a record, let's say. You could also, for example, new type all of the text and derive from there, and then you can at least have in your Servant specification, this header corresponds to this type, right? But nowhere have I ever seen within headers, Servant's documentation or anyone bother to mention that, by the way, this is a library of combinators. And there is not only nothing to stop you from writing your own combinators in order to do so and handle these types of cases, but here's how to go about it.
Yeah,
Right? Here's
if
how to
I
go
had
about
gotten,
writing some of your own combinators.
so if I had gotten that piece of information when I was working on this project, my code would probably be a lot less ugly and I would be a little bit less pissed off.
Additionally, there is also no reason for your combinators ought to be HTTP, right? It is a type-level combinator library. You could have a combinator that is, in fact, a single-page application route and write an interpreter for that, right? It is about the approach of saying, here, we have a library of combinators that are here for you to use that allow you to document your API in terms of types. What Yesod does is it actively blocks you from documenting your API in terms of types by maintaining a massive cardinality in order to avoid the problem. It's not about least power. I think Servant actually gives you more power. It just doesn't tell you how to use it. And that's certainly an
Right,
issue.
but if you don't tell me how to use it, what good is it?
Oh, I completely
Okay.
agree and acknowledge this. As a person who spends a bunch of time authoring Servant combinators, it's very annoying to me that this skill is not proliferated.
Right, okay.
But nevertheless, I'd just like to say I don't think it's least power.
Okay,
It's,
that's
actually
a very good
almost
insight, and I think that's worth. I appreciate the fact that you brought that up. I think that if I have to encounter Servant code again, that will make me hate life a little bit less.
Well, at the very least, you should take the time to consider the honesty of a type, right? Types are only as honest as we can make them.
Right.
And if the cardinality is ever higher than its runtime image, our type is dishonest to some degree. And what Yesod is doing is avoiding this problem through dishonesty. I would say that it's not well typed.
We might have to have a wrestling match about that later on.
I will do so, and I will bring butter.
Excellent.
All right.
Fantastic. Sounds like a great time.
I just think for the next conference, we should have like a developers MMA.
You're on. Anybody else? Yes, I have a repo with example code that you can run and execute and poke at. It's up on my GitHub. I'll send a link out to the Discord. I just need to push a few last-minute updates to it. But yes, absolutely.
Thank you.